Okay, so we've heard quite a lot from Daniele about how some of the things that we've talked about really arise in classical GR. And I'm going to sort of go even more basic than that and just talk about constrained Hamiltonian dynamics in a very simple-minded, straightforward way. Because that's what I think we need to do to get clear on some of these issues. So I disagree with some of the things that Daniele was saying when he was saying that what goes for time goes for space. I hope to show that, at least in the canonical formalism, that's not true. Okay. So here's a quote to motivate the topic of the talk. So there's a very recent paper by Sean Gribb and Karim Tebo, where they seek to connect the classical and quantum problems of time. So according to them, the quantum problem of time is that the canonical quantization of general relativity leads to a timeless formalism. And they think that this is a consequence of an incorrect treatment of the temporal symmetries of the classical theory. What's the incorrect treatment? Well, according to them, by treating local temporal labellings as entirely unphysical and changes entirely relational, we do not retain in the quantum formalism the full classical dynamics or the implicit temporal ordering structure. So in particular, when they when they criticize time being treated as entirely relational, they have in mind Ravelli's view and the view that Daniele was mentioning and I think endorsing earlier. Okay. So I'm not sure, I don't want to agree with them that what Ravelli says is incorrect. I think understood in the right way, it's the right thing to think. But I do agree with them that orthodoxy is wrong. And I'll say much more about what I take orthodoxy to be as the talk goes on. However, it's not clear, and this is the question I want to raise in this talk and not necessarily answer, that the canonical quantization relies on our understanding the classical formalism in a way that I agree with them is incorrect. So one question is, does canonical quantization, the quantization program that leads to something like the Wheeler-DeWitt equation, rely on this incorrect understanding of the classical theory? And in particular, if we do end up with the Wheeler-DeWitt equation, is it fundamentally timeless? So the way it's been presented, and the way Craig presented it yesterday, the idea is that we need to see time as somehow emergent. So we have a fundamentally timeless representation of physics, and then we somehow get out of that an emergent time. The time isn't fundamental. So what I want to suggest is that that's perhaps not straightforwardly obvious, and that you can think of the Wheeler-DeWitt equation as actually really involving time in some way, and what these programs and different ways of getting time out are not showing something that's strictly speaking emergent, but just articulating where time is in the Wheeler-DeWitt equation. Okay, so that's the outline. And here is how it's going to break down. So I'm going to start by reviewing orthodoxy, reminding most of you of some things that are fairly pedestrian and elementary, but I think it's worth going through some of the details because I want to draw some distinctions which I think are sort of crucial to understanding things in the right way, and to draw those distinctions I'll need to review some of these details. So once we've got orthodoxy on the table, I want to consider two challenges to orthodoxy. So one recently by Brian Pitts, and one by Julian Barbour and Foster. And to give the punchline away, we'll see that Pitts' observations are kind of orthogonal to the worry you might have concerning orthodoxy and its interpretation of canonical general relativity, but Barbour and Foster's insight is bang on target. So once we've understood what they're saying, we'll then think about the Wheeler-DeWitt equation. So I really don't have much to say about this, but what I want to suggest is that once we've gone through these two, we'll have a certain perspective on the kind of program that Tom Ashby was outlining yesterday. Okay. So, review of orthodoxy. So start off by just considering an unconstrained Lagrangian system. So here we have no apparent underdetermination. The physics, the formalism of the physics admits a fairly straightforward interpretation. So we represent possible physical histories as curves in configuration space. We associate to these curves the quantity of the action by integrating the Lagrangian along the curve, and we take the physically possible curves to be those that extremize the action. And we can convert this into a Hamiltonian theory, so we define the canonical momenta in terms of the Lagrangian in this way, and this gives us a map from the tangent space, the tangent bundle over configuration space to the cotangent bundle. It's a bijection, and if we define this object the Hamiltonian in this way, then the very same dynamics we had here can be equivalently represented in this way as first order equations giving us, for a point on phase space, a dynamical curve. And there's a nice geometrical interpretation of what's going on here. So the cotangent bundle comes equipped with, this is very annoying, hang on. Let's do this. So the cotangent bundle comes equipped with a certain canonical geometrical structure. And what this allows us to do is, given a function on the cotangent bundle, we can use this symplectic form to associate with it a vector field via this equation, and then we can use the symplectic structure to define a bracket operation on functions on phase space, and in particular this gives us a nice way of understanding the Hamilton's equations we had on the previous slide. Our physically possible histories are just integral curves of the vector field we get when the function is the Hamiltonian. And in particular, for an arbitrary function on phase space, we can represent its evolution along physically possible curves in this way. Okay, so I take it this is all familiar. Things are nasty, and we have the knotty interpretational problems when we have a system with gauge symmetries. So if our Lagrangian has a symmetry group which is parameterized by arbitrary functions of the independent variables, then we have these nasty properties. So from Nurse's second theorem, we have identities that hold between the Euler-Lagrange equations. And of course, when all of the dependent variables are subject to Hamilton's principle, these are the vanishing of these expressions are just the dynamical equations. But of course, if we have identities between them, this means that not all of those dynamical equations are independent, and we have an apparent breakdown of determinism. And if we try and go from this Lagrangian to a Hamiltonian representation of the theory, it turns out that our canonical momenta are not all independent. They satisfy the so-called primary constraint, so these identities follow just from the definition of the momenta in terms of the Lagrangian. And this means that the Hamiltonian dynamics lives on a proper subspace of the cotangent bundle defined by the constraint functions, and the dynamics are complicated. And here's what Dirac showed. So here's a way you can represent it. So you now define this thing, the total Hamiltonian, which is a Hamiltonian defined in terms of the Lagrangian in the standard way, but then we can add these additional functions. These are now the so-called first-class constraints. So these are the constraint manifold on which the dynamics lives is defined not just by the primary constraints, but there may be extra constraints you need to add on, just so that your dynamics is consistent. And then the first class constraints are just those constraints which have weakly vanishing Poisson bracket with all the constraints. And weakly vanishing just means that this thing is 0 on the constraint surface. And then our dynamics can be written like this. So we've got a Poisson bracket with this object, and then we have an addition, the Poisson bracket with the with the first class constraints. And these functions, the crucial thing is that these functions U are arbitrary, and in particular arbitrarily time dependent. So we have a clear apparent underdetermination, apparent indeterminism. So what do we do about this? Well, there's so this is just a nice sort of quick, simple way of thinking about it. So in the Lagrangian case, we've got curves for which the action isn't stationary, but between 2 points there are lots of curves for which the action is stationary. On phase space, given a point, there's no unique integral curve of a vector field which satisfies Hamilton's equations. There are lots of vector fields that satisfy Hamilton's equations, so we've got lots of integral curves of such vector fields passing through a given point. And the standard move in face of this apparent indeterminism is to use a very natural geometrical structure of the space on which the dynamics lives to define a notion of gauge. So in particular, the first class constraints partition our constraint surface, and if we just stipulate that points on the same gauge orbit, where a gauge orbit just is the set of 2 points that can be related by a transformation generated by the first class constraints, then we get back determinism. And equivalently, we can think of, we can stipulate that only functions on the constraint surface which are constant on gauge orbits represent genuine physical quantities. If we do this, in nice cases, we get back a deterministic dynamics. So in a slogan, the orthodox position is first class constraints generate gauge transformations. And the geometrical interpretation is that if we consider the induced, if we restrict the symplectic form on the cotangent space, on the cotangent bundle to the constraint surface, we get a presymplectic form, and the gauge orbits are just those points related by curves whose vector fields are in the kernel of the presymplectic form. Okay. So the orthodox position is the gauge orbits are collections of, the points on the same gauge orbit are physically equivalent. So here's a couple of statements of this position. So here's John Ehrman attributing it to Dirac. Ehrman says Dirac proposed that gauge transformations be identified as transformations generated by the first class constraints, and by gauge transformations here we mean that 2 points of phase space which are connected by such a transformation are regarded as representing the same physical state. And later in the paper he endorses this view, and in particular says, in our account of the results of observations and measurements, we should understand these things to be, the results of observation should be expressed by values of the observables, and by observable he means quantities that are constant on gauge orbits. And here's Bianca-Dittrich expressing the same view. And what's crucial about this, so in this, this is a paper where she's talking about Rabella's complete observable and partial observables program. But here she is endorsing, even in the context of a totally constrained system like general relativity, the view that phase space points related by gauge transformations, where by gauge transformation she just means a transformation generated by the constraints, they describe the same physical state. So even in the context of general relativity, she is ostensibly endorsing orthodoxy. Okay. So, and this leads to the problem of time in a sense that I think is more radical than has been acknowledged in the talk so far. So why does it lead to the problem of time? Well, in the context of GR, the transformations that generate evolution are gauge transformations in the technical sense here. So you're saying of two states that you would like to think of as different points on a single history, that they represent exactly the same physical state. And if they represent exactly the same physical state, nothing has changed. If physical quantities have to take the same value on all points related by such transformations, then all physical quantities do not change. They take the same value at every point on a dynamical trajectory. So this is more radical than than I think has been suggested in talks so far, and in particular there is a clear disanalogy between time and space here. So in the spatial case, you can so you implement three diffeomorphisms are also gauge transformations in this sense, and this says I want to regard 2 points which represent 2 points which correspond to different Riemannian 3 metrics on the same base manifold as representing the same state. Well, that's just to say a given point of the phase space should not distinguish two geometries which differ merely on where the 3 metric is placed on the fundamental 3 manifold. Okay, that's not getting rid of space. You still have 3 geometry. But here, if we do the same for so let me draw a picture. I mean, we have space-time, and we have two different slices through it, and these 2 slices correspond to points of phase space related by a gauge transformation, and we're saying that these represent the same physical state, right? The diffeomorphism constraint says, imagine 2 space-times which you put the space-time metric on the manifold differently. So in particular, this geometry is the same as this geometry, but they just differ over which points of space-time the metric lies on, right? That is physically equivalent to that. Well, that's a sensible thing to say. That's physically equivalent to that. That's not a sensible thing to say.
Sorry, the 2 slices refer to a totally arbitrary foliation in a totally arbitrary coordinate time. So why would you?
No, you can think of this in a coordinate-independent way. So it's, I mean, thinking about it in a coordinate-independent way, we're thinking this slice has the same 3 geometry as this slice, but it differs in terms of which manifold points it's on. And we want to say that that's not a physical difference. And in coordinate language, that could just be I've got the same 3 geometry, but I've differently coordinatized it in terms of my spatial coordinates. Right here, we have 2 different 3 geometries. And if we take seriously the idea that gauge transformations in this technical sense are gauge transformations in this, the points of phase space they relate are physically equivalent, we're saying that this geometry doesn't correspond to a different physical state than this one.
Because they're related by time-like difference.
Yes.
The statement is because you can relate the 2 phase space points. It's not only the 3 metric, it's also the extrinsic property.
Right.
Because they are related by time-like difference, according to the orthodoxy, they are the same physical configuration.
Right. And you're happy with that?
Pretty much.
Okay. Well, I mean, if you're not happy with that, I want to show you a way out. Yeah.
The same physical state, do you mean numerically identical, or do you mean...
So they're distinct points of phase space, but the interpretation is these are gauge-related points of phase space. They're 2 points that are just different mathematical representations of the same physical state.
Meaning numerically identical physical state?
Yeah.
Single physical state?
Yeah.
Not just
that they're...
Logically identical.
Okay. So now on to the ways of avoiding challenges to the orthodoxy. So let's start with Brian Pitts. So there's this paper in Annals of Physics that's recently come out, and he also has another one discussing GR. So he in particular discusses electromagnetism. So here's how electromagnetism looks when we cast it into this machinery. We have the familiar Lagrangian defined in terms of the Faraday tensor, and if we do the kind of thing we were sort of showing on previous slides, we get this as our Hamiltonian, and the variables are the electromagnetic force potential and the momentum associated with it. And in particular, the momentum is related to the Faraday tensor in this way, so it corresponds to the electric field. And we get the vanishing of the time component of the momentum as being a primary constraint, requiring that is conserved by the dynamics. It gives us a secondary constraint, namely that the divergence of the spatial part of the momentum vanishes. So this looks like the divergence of the electric field is zero, which is what you want. And if you look at the transformations generated by these, then it looks like they leave naively the electric and magnetic fields invariant. So that's what you would do. In particular, they leave the momentum unchanged. So these constraints, the transformations these generate, leave the momentum unchanged. So it looks like they should leave the electric field invariant. But they don't. So this is Brian's observation. So what do they do? Well, he says, why don't we just crank the handle? So first of all, let's consider the transformations generated by the vanishing of this, or sorry, this constraint. And if you take the Poisson bracket of the force potential with a smearing of this, then you get this. And if you then sort of calculate the Faraday tensor, so this is your expression for the change in the A as a result of the transformation generated by the constraint. If you then plug that into your expression for the Faraday tensor, what you get is that there's a change in the electric field. Right? And in particular, if the electric field changes in this way, then the divergence, the vanishing of its divergence needs to be conserved. And exactly the same thing happens when you consider transformations generated by this constraint. Again, we get that the divergence of the electric field vanishing needn't be conserved. So this looks like a bad physical change, right? So what happens, what we could do, and this is what Brian does, is let's just put these two transformations together. So we've got the general expression for a transformation, a change in A generated by first-class constraints. And if we require that the electric field be unchanged, then what we have to do is set these two smearing functions to have this relation. So the time derivative of one has to be the negative of the other. So if you tune the transformations you make that are generated by each of the constraints in the right way, then you get that things are invariant as they should be, and you actually get out this expression for the change in A, which is just the kind of gauge transformation that you think should be allowed. So has this shown that the orthodox view is wrong? No. So here's what's going on. So if I take a solution to my theory, and I act on it by a first-class constraint, an arbitrary first-class constraint, then it will send it to a curve, which may not be a solution of the theory. Right? That's what Brian has shown. But that doesn't undermine the interpretation of all points on the gauge orbits as being physically equivalent if, for every such point that I get mapped to, there is a solution, and only one solution that passes through that point, which is physically equivalent to this one. Okay, so for each point, if this is an arbitrary gauge transformation, then a different solution to this one will, well, actually, I could have found one that passed through these 2 points, of course. But the point is that just by showing that the dashed red line, in general, isn't a solution, well, doesn't correspond to a good physical change from the original solution, doesn't undermine the idea that every point on here is physically equivalent. So orthodoxy is untroubled by Brian's observation. So far we've seen no good reason to give up the interpretation of the gauge orbits.
So what you're saying is that what is missing the analysis is the fact that you have to project on solutions of the equations of motion. It's not enough to just consider arbitrary gauge transformation, then you have to check what happens on shell.
Yeah.
Yeah. Because the orthodoxy is a statement about on-shell configurations in the classical theory. Do you understand correctly?
Well, so I think it'll be clear whether, if you consider where orthodoxy comes from when you consider the way Dirac motivated it, then the way I would prefer to put it is that the orthodoxy is a statement about how you should regard, how you should interpret these transformations understood as point transformations. Whereas what Brian's considering is how you should understand the transformations when you understand them as acting on curves. If you consider their action on curves, then it's not necessarily going to take a curve that's a solution to a curve that's a solution. But if it does take it to a curve that's a solution, then it will take it to a physically equivalent one. Okay, so the second challenge, and the one that does have a deep moral for this, and does tell us that we don't have to accept what Daniele suggests we should and think of this and this as physically equivalent, is the one given by Julian and Brendan Foster. So when you Google Brendan Foster, that's the only picture that comes up. But that really is him.
You're not doing him a favor, you know?
I think that's
doesn't add to the credibility of the argument.
Yeah.
Depends on your point of view. For some people, that might be an enhancement of credibility. You can do something else other than academic.
I think I can send you a picture of him.
Yeah, I could have looked harder. But this was just a few hours ago, and that's the only one I find. Okay, there were lots of other pictures, but they weren't of him. Right. Okay, so let's start by considering Dirac's argument to understand Julian and Brendan's objection to it. So Dirac says, consider an arbitrary function on phase space and consider its evolution. It's the change in the function under an infinitesimal increment of time. So we get it by, that's given by this expression, and g dot is just the thing we had a few slides ago, and in particular, this breaks down into these 2 bits where we've got this bracket with the constraints, and these v's are arbitrary. And because those v's are arbitrary, we could have chosen a different h total Hamiltonian with different v's here, and we would have got a different expression here involving a different v prime. And if we subtracted them, then we get, under these infinitesimal temporal evolutions of g, a difference in the g given by this. And this, because this is infinitesimal, this just looks like the expression for an infinitesimal change in g generated by under a transformation generated by one of the first-class constraints. So if you think that under this infinitesimal temporal evolution, physical quantities are unambiguously defined, that the physics is deterministic, you better require that your g there's no delta g for such a transformation. Now, of course, what's key here is that we're considering a change in g after a short time. So we're evolving it by an infinitesimal time increment. So in pictures, here's what Dirac's considering. He's starting here, and he's considering evolving by delta t and evolving by delta t, and noticing that the different places you end up are exactly related by a transformation generated by a first-class constraint. Now, of course, in order to say the physics is deterministic, and therefore this state must correspond to this state, it better be that this state can be identified with this state, and that requires that we have started somewhere and gone a fixed amount of a meaningful physical time. And because we've gone a meaningful unit of physical time, where we've ended up under these two evolutions better be the same place. But what if our theory doesn't involve a meaningful physical time? What if the temporal parameter in our theory doesn't have a physical meaning, or doesn't have a metrical meaning? So let's go back to configuration space and consider two different ways you might have some kind of redundancy in our formalism. So one is we might have some configurational space redundancy. So we might have a group action on configuration space, and we might think that all of the points related by the group correspond to the same physical configuration. And so in particular, if we've got a theory respecting that physical intuition, then the action assigned to this curve and the action assigned to this curve, assuming that they intersect the group orbits under similar increments of time, should be the same. So our physics shouldn't distinguish between these two curves. But there's a different way we might have some redundancy in our theory. We might have reparameterization invariance. We might think that the temporal parameter with respect to which we express the evolution doesn't include physical duration information. So in particular, if we think that, then what's significant is the sequence of configurations and the order they happen in, but not when, with respect to the parameter time, they occur. So the action associated with the curve parameterized by the green dots and the action associated with the curve parameterized by the red dots should be the same. And it's exactly that kind of redundancy that leads to the Hamiltonian constraint being a constraint in GR. That's not quite true, and I will acknowledge the extent to which it's not true in a slide or two. But if you've got this kind of redundancy, then it undercuts Dirac's argument, because he's saying we should identify this point and this point because they're where you get to after the same amount of time. But if our t isn't time, or if it doesn't give us if the same delta t can't be interpreted as a physically meaningful unit of duration, then we've got no reason to think that this point and this point are distinct states at the same time. They may be states that lie at different places on the same curve. So in particular, you could have a reparameterization-invariant theory that looks like I'll show you in a slide or two. But just before I show you that picture that hopefully will make things clear, here's a quote from Henno and Teitelbaum, who acknowledge exactly this distinction. So they say of Dirac's argument, and the argument that says you should treat transformations generated by first-class constraints as gauge, a word of caution is needed. We've been implicitly assuming that the transformations that implicitly assuming that our parameter corresponds to something observable, that it's a physically meaningful time. You can also take the point of view that the gauge arbitrariness indicates that time itself is not observable. So that's what we've been discussing. So here's a very simple theory where you have exactly this kind of redundancy. So it's one that Junior Barbour likes, talking about Jacobi's principle. So my Lagrangian is just this expression. This looks like the kinetic energy, but it's defined with respect to this arbitrary lambda label. And B is the normal potential. And this this action is invariant under reparameterizations for fixed configuration points. If I change my parameter label by an arbitrary if I just change it arbitrarily but respect the ordering, then the value of the action will not change. And in the Hamiltonian analysis of this theory, it turns out that the Hamiltonian is vanishing, that it's given by this expression. And yeah, where h is this, so h is a constraint. So this vanishes uniquely given the definition of the momenta. And if you think about what this looks like on phase space, we get something like this. So our gauge orbits are now one-dimensional. And our dynamical trajectories just lie on gauge orbits. Now, because the geometrical structure of this phase space is a pre-symplectic structure, it's true that we can think of it like this. We can think of dynamical curves as vector fields satisfying this equation. And because this vanishes and this is a pre-symplectic structure, this is there are lots of different vector fields that satisfy this, but they all have the same image. So all their integral curves have the same image. All that differs is the parameterization they induce on those paths in phase space. So there's no apparent determinism. There's no need to say this point and this point are the very same point, right? If we regard functions that vary along the gauge orbits as representing physical quantities, there's no indeterminism, right? At the level of functions on phase space, we get an unambiguous sequence of different physical states. The only thing that's undetermined is the rate at which we get those with respect to the parameter, right? So that's unphysical. But to regard, we don't have to think of this point and this point as the same physical state to get rid of the unphysical, to acknowledge the unphysical nature of the time parameter. So there's just no pressure in a theory like this to regard this and this as the same physical state. And so if I have a fixed foliation, then there's no pressure to regard this state and this state as the same physical state, or that geometry and the other slices correspond to the same physical state. Okay, so just to summarize where we got to, yeah, how long have we got?
Till about 6 o'clock.
Okay, so that's good, because the last bit of the talk doesn't really exist, so that's going to go back.
Really? Because if we do that, we'll have no time for the runtime.
Yeah,
That math can't be right.
Okay, so we started at 5 past. So okay, 10 to 6.
5 minutes.
Okay. So far we've come across two different types of gauge transformations. So we've got maps on phase space that map us to physically equivalent points. And we can have a theory which, as solutions, allows us, starting with a given point, it has as solutions curves which have distinct paths in phase space. And we get rid of the indeterminism by saying there are classes of points which are physically equivalent, and although we have different paths, they all intersect the same gauge orbits in the same way. We also can have a transformation that leaves images of solution curves invariant, but just changes the parameterization. So they're the two we've seen, and if our gauge transformations are of this latter kind, there's just no pressure to require that physical magnitudes weakly commute with the constraints that generate those transformations. Now, of course, in GR, we can't analyze, unless you want to buy into the shape dynamics program, we can't reduce all the gauge redundancy to one or other of these two things, because we have refoliation invariance, which doesn't fall into either of these groups, because if we refoliate space-time, that gives us a curve in phase space which corresponds to a different path, and we want to say that's the very same space-time, that's the very same physical history, but unless we want to end up having to identify this three-dimensional geometry in this one, we can't say it's the very same path, that path corresponds to the very same history, because point by point it involves the same sequence of physical states. Okay, so finally time and the Wheeler-DeWitt equation. So what does this distinction between these different types of gauge transformation, what light does that shed on interpreting the Wheeler-DeWitt equation? And are Karim and... so I hope I've made it clear that there's an interpretation that's appropriate for transformations on phase space that correspond to configurational redundancy, which is not appropriate for transformations that correspond to reparameterization invariance. I haven't managed to say anything about refoliation invariance. But if you treat the latter two in the same way that you treat the former, then you're doing something that clearly seems physically crazy. But do you have to think of those transformations in that way to buy into Dirac's constrained quantization program? So that's the final question I want to raise and not answer. So, first of all, let me remind you of the block universe. Right? So, in the block universe, we have a representation, according to people who defend a B theory of time and change. Right? Although this, as our representation of the universe, doesn't change, it doesn't evolve, it's a representation of an evolution. Right? Different points in our block correspond to events occurring earlier or later than others. So it is a picture of evolution, even though it itself doesn't evolve. So the question is, why can't we think of the Wheeler-DeWitt equation as basically representing, although the Wheeler-DeWitt wave function doesn't evolve, why can't we think of it as representing real evolution without it itself evolving? And why can't we understand all these well-known programs to extract time from the Wheeler-DeWitt equation as not showing it as emergent from a fundamentally timeless representation of reality, but just uncovering where time is in this representation of reality? So, how do you get the Wheeler-DeWitt equation? Well, yesterday Tom reviewed very quickly Dirac's constraint quantization program, so I'm not going to go through that again. And what you require is that physical states are invariant under transformations generated by the quantum constraint. So you promote the functions, the first-class constraint functions on phase space to operators, and you require that they annihilate the states, and it's only those states annihilated by the transformations, by those quantum constraints that are deemed physical. And then you have to define an inner product on those and complete it to form a Hilbert space. But the basic thing is that the quantum constraints annihilate the physical states, and so transformations generated by the quantum constraints leave the physical states invariant. So the question is, what notion of gauge legitimizes this move? So in particular, we saw the Hamiltonian constraint. We said, on its action on points, it takes us from point to a physically distinct point. It's genuine evolution, but acting on the curve, it leaves it invariant. Right? So when we get to the Wheeler-DeWitt equation, can we think of this as corresponding to what we have in the classical case, where point to point we get genuine evolution, but acting on the curve, we don't get any change. So in particular, corresponding to the classical case of going from a point to a point that you regard as physically distinct, what's wrong with a naively temporal, and I would suggest you think of this in Everettian terms, understanding of transition probabilities between components of the Wheeler-DeWitt equation. So you have the Wheeler-DeWitt equation, it's a big superposition of states which are not physical states, right? And the Hamiltonian constraint will take you from one to a superposition of others, right? And from those you can read off transition probabilities, but its action on the whole bundle of them leaves it invariant. So I'm going to stop there because Kerry's stood up, but let me just leave you with a quotation where this is from Bill Unruh, sort of basically objecting to this kind of way of thinking about things, and you get similar statements from Carol Kukash and others. I think this is in line with what Ravelli says about partial observables and what he says about operators corresponding. So the operators that give you these quantized, the volume and area operators, projections associated with those will take a physical state to something which isn't a physical state. But that's fine. You should think of those as being genuine, corresponding to genuine physical magnitudes, because you don't have to regard physical magnitudes as constant on curves like this. Okay, thanks.
So just a couple of minutes for questions. Yeah.
So first, thanks for the talk. So first, just a call for distress. I mean, I'm usually reproached because I challenge the orthodoxies and quantum reality. For once, I just limit myself to reiterating the orthodoxy about diffuse and so on. Someone stands up immediately afterwards and that's wrong. Okay. That was quite cool. So let me just understand. So there are three aspects. One is, are you saying that there is a totally equivalent statement to the one you're making about the Hamiltonian constraint in a covariant language? So if I were just considering four-dimensional metrics and four-dimensional diffuse, would you say that there is one of those diffuse that I shouldn't really mod out because that is physical?
No.
So there's something that must go wrong in the standard translation of the covariant picture into Hamiltonian analysis.
So I need to think that through, but in considering the covariant, so in the covariant case, you want to be summing over four geometries.
So even at classical level.
Yeah.
So forget about summing geometries. I mean, just Lagrangian geometry.
Yeah.
So we have a six-dimensional metric space.
Yeah.
And then we have four-dimensional
Yeah.
diffuse.
Yeah. Yeah. So no, I want to say. So you can think of you can do things on the space of solutions, and you've got a that has a presymplectic structure, and the four diffeomorphisms are. If you want to mod out by those, you want to completely mod out by those.
The result has to be the same, and you end up with equating, putting equal in physical terms those two configurations. Because there will be two different space points that correspond to the same four-dimensional geometry.
Right. So here's so consider this different foliation, right? One and the same four geometry. So I've already collapsed it down to a single four geometry, and now I'm considering different foliations. So this gives me distinct paths in phase space, and I want to say I agree this path is physically equivalent to this path, but I don't want to have to do that by saying, and here's how it's equivalent. This point is equivalent to this point, is equivalent to this point.
Okay, but then it becomes a problem of translation in canonical language, what is a physical statement about the absence of any preferred time direction. And I may agree, it may be very subtle in the way you actually encode this statement in canonical Hamiltonian analysis, and one has to be careful.
Yeah,
I agree with that.
That's the point. I certainly don't want to say that these paths correspond to different physical histories.
So I think we agree then on the physics. We may disagree on the fact that we add or not have an issue in stating the physics. In
I don't think she really believes it, but the quote from Bianca Dittrich is precisely saying these 2 points are physically the same state, which is saying this 3 geometry and that 3 geometry are the same.
Probably we're talking about.
Friendly enough terms with Bianca, and if I disagree with this publicly, she will beat me up. So